Morning, everyone. So we're going to continue on with the energetics chapter that we started yesterday. Today we're going to focus in on actually formulas that actually address this notion of heat. Heat is sort of a measure of energy that's being passed. It's thermal energy that goes from hot to cold. We're going to start off doing a quick recap of just kinetic molecular theory, the three common states of matter. We're going to figure out which are endothermic, which are exothermic, and then we're going to look at our formula on heat transfer. This part here will look a lot like a physics lesson. We're just going to introduce the formulas, introduce some of the terminology here, and then tomorrow we're going to apply this stuff back to our chemistry course. So let's start off here with heat. Let me actually start off with the definition here. Heat, by definition, is energy transferred between an object with high internal energy. That can more easily be saying, oh, this is from a hot object to something that has low internal energy, which is traditionally cold. So heat is implying it is a transfer. So if I have, let's say, two balloons, one balloon here is really, really hot. The particles are zipping by really quickly. One balloon here is filled with a really cool gas, colder gas here, not moving as quickly. I can't ask you, what is the heat of this balloon, or what is the heat of this balloon? Because heat implies it has to be a transfer. Heat has to be a sort of a energy moving from one place to the other. We only get heat when we have two objects. In general, when objects are different temperatures, when the average kinetic energies are different, heat is actually going to be the energy that actually passes. Based on another law of thermodynamics, it always goes hot to cold. So heat is actually in this transfer here. I just want to show you, just like last day we talked about enthalpy, and we said I can't tell you the enthalpy of just the system. There's way too many particles. In this case here, I can't tell you just the heat energy in the system because heat implies a transfer. So that's what heat is. That's going to be our main concept in today's lesson here. Let's just do a quick recap here. These heat transfers can ultimately result in a change of state. So let's just have a look at kinetic molecular theory. This is sort of a theory that you were introduced back in your junior science courses here. Basically, it says everything is made out of small particles. The particles are always moving. They're always vibrating and slipping and sliding depending on the state of matter. Let's just recap some of those changes in state. So we have three common states of matter, which is a solid. Basically, the particles are very rigidly packed together. They're just shaking, vibrating in place here. As you then heat it up, we can gradually gain the temperature, and we can gradually transition this solid here over into the liquid state. Liquid state, it's the same number of particles, so I drew 6 particles, but because the particles now have more energy, they're starting to actually slip and slide past each other. They're actually going to move a little bit quicker. They've overcome some of those intermolecular forces, so I like saying slip and slide for liquid. If you keep heating it up here, the particle gradually move faster. It gets hotter and hotter. Notice that there's actually spaces between particles. And eventually, those spaces get to be so large, the particles can actually overcome the atmospheric pressure that's trying to keep them in the liquid state. And eventually, the liquid will eventually change into the gas state. And gases, I like saying, they're fast and far. So they're moving really, really quickly. They're zipping around, and they're sort of not localized to any given container. These are the three most common states of matter here. These states of change here, I already alluded to, whether I'm inputting heat or really releasing heat here, we can actually use the terminology of endo and exo again. So in this case here, let's say I go from solid to liquid, I would imply, oh, I need to actually heat that up to actually make that to occur. So in red here, I'm going to do, red is going to stand for endo. Basically, this is going to require a heat input. This is going to be a system that actually absorbs energy. So in this case here, we're going to say melting. Make sure you know these phase changes here. These are all what are called physical changes, because if I imagine this is water, so I have H2O before, I still have H2O afterwards. H2O itself inside, it's covalent and it's bent and it's polar and all that. But really when I'm heating it, we're going to see towards the end of this lesson here, basically all I'm trying to do, I'm not ripping the water molecule apart. It's still going to be water molecule. But I'm basically heating up enough that I can overcome those intermolecular forces. Hopefully you can remind me the intermolecular force this time is hydrogen bonding, really, really strong. And therefore it then becomes a liquid. So that's the melting process. How about going liquid to gas? This one here is called boiling. Sometimes you can also say evaporating. I don't know if you ever thought about this. What's the difference between boiling and evaporating? They both stand for liquid to gas. If I had a room temperature glass of water, would you say that it's boiling or would you say it's evaporating? Hopefully you were able to say here at room temperature water here, you will have evaporation. You will have liquid becoming gas state, but it definitely doesn't refer to all the particles all at once. You might just have a lucky fast-moving particle. It happens to sort of breach the atmospheric pressure. Oh, it lucks out, it jumps into the gas state, but that's definitely not true for the majority of particles. For boiling, we've actually heated up enough. All the particles on average have heated up enough so that by 100 degrees for water, all the particles have enough kinetic motion, kinetic energy to actually overcome and breach this atmospheric pressure. So that's that difference between boiling and evaporating. There are some chemicals that actually skip the liquid state altogether. It doesn't mean change the liquid state really quickly. In fact, we're at a pressure where it doesn't convert to liquid at all. We'll call that state here subliming or sublimation. An example of that would be dry ice. Dry ice is actually not water at all. Dry ice is actually solid carbon dioxide. We are actually under a pressure condition that carbon dioxide actually never liquefies. So what's going to happen is dry ice, I think the subliming point is like -60, -70 degrees or so. So they use it on movie sets a lot here. They pull out this really, really cold dry ice as they just sort of expose it to the atmosphere. The atmosphere is sort of much warmer than it here. It's much past the subliming point here. And that solid carbon dioxide just vaporizes. It becomes a slight misty effect here. And all that's just pure carbon dioxide. We can actually form liquid carbon dioxide in the lab, but we'd actually need to play around with pressure. I can't be at the 1 atmosphere pressure that I'm at right now, but I can artificially create a container where I can actually change the pressure on it. You can liquefy carbon dioxide, just not under regular conditions. So that's subliming. That's an example of something that skips the liquid in our regular conditions. Let's do in blue here. Blue is an exothermic reaction, and this is heat when it's released. So in this case here, going from gas to liquid, let's say on a cold day, you breathe onto a cold window pane, you see little droplets of water form. We call that condensation. So condensing is going from gas to liquid. Liquid to solid, you can call it freezing. So water freezes, becomes ice. You could also call it solidification. It's forming a solid. That's perfectly fine. Back when I was learning this, I would call the reverse, gas to solid, also subliming. You may hear a really archaic term, fugation. Nowadays, I think you call it depositing, or it's deposition. But that, again, skips over to the liquid state all at once and basically just jumps the state there. Remember these phase changes here, or you can call them state changes. Remember, I prefer the language of phase because it's possible I may have different allotropes, different sort of structural formations of ice. You can have ice 1, ice 2, ice 3. So those are all different phases, but they're all ice, solid. So phase is a little bit more generic of a term here. Phase change here, just a note here, this is a physical change. Nothing has actually happened to the actual bonding. It's the exact same H2O before, exact same H2O afterwards. So definitely know the names of these state changes here. Definitely know which ones are exo and endo. If you totally blank out, what you can do is you can think of it as a reaction. So let's say I go gas to liquid. Ask yourself which side has more energy. We know it's a physical change, so not surprised it's water and water. But what's happened here is gas has become liquid. I would argue gas has more energy. Liquid has less. The energy has to go somewhere. So in this case here, if I start off with $100 and now I'm only left with $20, where'd the other energy go? Well, the other energy had to be a separate plus heat term, and therefore the plus heat term is actually on this side here, so therefore exothermic. So you can do that as a nice memory aid here. We can actually do this as an experiment here. This is actually going to give us, you've probably seen this before, it's called the temperature time graph. So let's just have a look here. So a temperature time graph or a temperature time plot. The experiment itself is fairly simple. I'm going to take out a hot plate. I'm going to have a ice block just sitting on this hot plate here, and I'm going to have frozen a thermometer inside. That thermometer here is still surroundings. It's still measuring what energy is being given to this ice block here. And my experiment, quite simply here, involves just cranking up the hot plate, and I'm just going to apply heat to this ice block. What I'm going to plot is I'm going to plot y against x. I'm going to plot the temperature on this axis, and I'm going to plot it against the time as this experiment goes on. So starting off here, let's say this ice block here starts off at, -10 degrees Celsius. So it's a cold ice block. It's below the melting temperature. That seems normal to us. I start that clock at 0 seconds. Over time, heat is actually being transferred into the system. As I transfer in heat, heat allows the particles to absorb that energy endothermically. the kinetic energy goes up, it starts shaking a little bit harder. That's sensed on the thermometer as an increase in temperature. In fact, the increase in temperature occurs really, really steadily. The slope is something called the specific heat we're going to see in a second here. But basically, it's going to heat up. The particles are just going to vibrate harder and shake harder. Surprisingly, as you run this experiment for longer, there's going to be a region where this temperature here actually plateaus. It actually flattens out. It's a little bit strange. You might have imagined, oh, I'm cheating. I actually turned off the heat source. When in fact, no, all the heat, by the time you get to 0 degrees, you are still transferring a bunch of heat. It's just that the particles themselves are not vibrating harder or shaking harder, changing the average energy. The average energy seems to have stopped. You heat it up a little bit more, phew, the temperature then changes again here, but suddenly again there's another leveling off region for a pure substance here. This one here occurs nice, like a flat plane like that. There's a weird temperature plateau before it ends up going up again. So we refer to these guys here as temperature plateaus, and the first question is, well, why are these as plateaus? I tried to give you a hint here. For water, as an example, I mentioned it's an ice block. For water, the plateau happens at 0, happens at 100. What's so special about 0 and 100? Hopefully you were able to say to me here, for ice, it melts at 0. We decided 100 to be a boiling point for water here. That's when we're actually changing state, when we're actually changing phase. So temperature plateaus, and basically the reason for that here is all the energy I'm adding, it's not like I cut off the heat source, all energy is used to overcome the intermolecular forces. Again, remember this is a physical change. I'm not actually breaking any bonds or anything, but I'm just pulling the particles hard enough. Earlier I started from, let's say, a solid state here. The particles were at -10. They were just starting to vibrate and shake a little bit harder. At 0 degrees, they're actually shaking hard enough that when I apply heat to it, I can actually pry these particles here, one from each other. I can actually start moving them farther and farther apart, and eventually I'm going to end up with the liquid of that. So overcome intermolecular forces, or in this case here, changing state. So what I'm saying here is, on the left-hand side here, we have 100% in the ice form, so it's 100% solid. By the time we're at 0 degrees on the other side, we're actually 100% as a liquid. Now this is the ideal case. I mentioned for pure substance, this one here should be a nice flat line. It shouldn't actually be able to change its average energy until all the particles actually convert state. In this case here, if you really did this in the lab here, the heat unfortunately is only being delivered sort of to this bottom part of the ice block here. The heat is not transferred evenly. In that case here, you might end up with a more sort of broadening, a little bit more of a curvy nature. It does flatten out pretty obviously, but it's not flattening out at nice uniform temperature. And chemists will actually utilize this, and they're actually to say, we expected the melting point to be some exact temperature, and in fact, in this case here, it was because the heat wasn't delivered very evenly. It's possible that the ice is also embedded with a bunch of impurities. The ice should melt at 0, but maybe the impurities don't melt there. We actually track this melting point broadening here to actually figure out the purity. So in this case here, let me actually write that down in words here. Melting point might broaden. Right? It's supposed to all happen at one single temperature because that's already enough temperature to rip apart the structure. Melting point might broaden if heat is not transferred evenly. So like this hot plate here, I'm only heating up the bottom part here. It's taking a little while for the heat to even pass to the top. Or if the sample is impure. So if I have some things that melt first and some things that melt afterwards, in general, we do this a lot in organic chemistry. You performed a whole long organic mechanism. It's really complicated. You produce what you think you produce. You then purposely melt it. And depending on sort of what temperature it looks like it started to liquefy, what temperature it looks like it's all liquid, we want the broadening to be as close to 0 as possible. That means I produce a very, very pure product. If the broadening is some like 6 degrees, 7 degrees or so, it's actually less and less pure. So that's what we're going to generally note here. It may not seem like a lot of heat, but again, once you do this with math here, it's actually quite a ridiculous amount of heat that's actually needed to do this. Once we're all liquid in a perfect scenario, the particles are now all slipping and sliding. You gradually add heat to that still, and the particles do. Average energy goes up, and therefore it then heats up. So let's do this a little bit with numbers, and then we'll come back to that graph there. This again here is a formula that I'm borrowing from physics, and we're going to apply this more so in the chemistry context. So heat transfer, you can use Q or capital Q, it doesn't really matter. The heat transfer, the amount of heat passing from hot objects to cold objects, depends, or it's a relationship between three things. It's a relationship between mass, m, relationship between a constant called specific heat, c, and heat transfer here, I would expect here to change temperature. So this formula here, Q equals MCAT, it is on your data booklet here. Let me just imply some of these terms here. Q, we're going to use this heat energy. For energy, depending on your context, you either use joules. In the context of moles, we may actually have kilojoules worth. M here is going to be mass. The SI unit for mass is supposed to be kilograms, but usually in chemistry, again, we do grams. C, like I mentioned, is going to be a constant. This constant, as written, currently is called the specific heat capacity. It's a constant for that material. Some materials are just easier to heat up. Some materials are just harder to heat up. This number describes the material itself. It's going to have a funny set of units we're going to see in a second here. And then when we transfer heat to an object, we expect either the temperature go up or the temperature go down. If you transfer more heat, we expect that temperature change to be more dramatic. When I look at constants like this, whenever I see the term specific, it usually means that the mass term is sort of isolated, factored out as its own. In chemistry, we're going to see it this way. In physics, sometimes you're going to see it generally referred to as just a heat capacity, not specific heat capacity. And without that term specific, it means that MC term is actually put into just a single constant. So just be careful of how they word it here. When they say specific, they actually mean the mass term is actually pulled out. Let's have a look at a specific heat capacity. So specific heat of water. It's going to turn out that specific heat actually is going to matter depending even not just on the chemical, not just on the material, but also on the state. Specific heat for water is actually 4.18 or 4.2. It is a funny set of units, joule per gram Kelvin. Let's take apart that here. I want you to imagine this per gram bit here is, imagine having 1 gram worth of water. It's liquid. Imagine having a thermometer inside. Imagine transferring the heat needed enough to jump up 1 step on the Kelvin scale. This specific heat here tells you how many joules, this 4.186 with the top unit here. I need 4.18 joules to heat up that 1 gram block of material by 1 degree on Kelvin scale. So that's 4.18. Let's compare that to another specific heat. I know here, the specific heat for aluminum. Aluminum is a metal, so it's going to be solid. This specific heat for aluminum as a material is only 0.9 joule per gram Kelvin. So that very same, imagine I have 1 gram worth of aluminum. This time it is a solid. I stick my thermometer inside. I want it to go up by 1 step on the temperature scale. This one only requires 0.90. So hopefully you're able to show me here is, because 4.18 is a bigger number than 0.9, that implies then the water is actually harder to heat up, whereas the aluminum is actually easier to heat up. Because this actually gives you how much energy you need to heat up that very same gram of water by 1 degree. So the bigger the specific heat, the harder it is to actually heat up. We're actually enjoying this on the west coast here. This is a nice sort of geography application. On the west coast here, let's say this is our shoreline. Let's say we have the water. We're getting pretty close to the summertime here, so water, and this is land. We're getting pretty close to the summertime, so basically the sun is at a certain orientation that it's actually sort of directed towards the land. It gets sort of hotter. In this case here, the sun is going to strike the land and the water. In this case here, because the land has a easier to heat up, as a lower specific heat, the land is actually generally going to get really, really hot, whereas the water, because its constant is relatively big, the water, although being warm, it's only going to be some moderate, some sort of medium temperature. In that case there, because there is a temperature differential, we're going to get a steady breeze, maybe not necessarily a wind. It's not like you're going to constantly get a wind blowing offshore, but we're going to get a steady breeze that basically cools down. The air above the land, which is really hot, is going to be cooled down because there's going to be a nice general flow towards the water. That prevents the land from getting really, really hot in the summer times. Let's say closer to the winter times here. In the winter times here, we get less intensity, less heat radiation here. The land, again, the constant is very low. The land is going to get a lot colder, but the same constant, it's going to take a lot of energy transfer for the water to actually cool down. It doesn't cool down as much. Again, it will feel colder, definitely, than, say, in the summertime. But based on that sort of more moderate temperature here, the steady breeze will now flow the opposite way. The water will actually sort of control our climate a little bit. It's going to prevent us from getting overly hot in the summertime. In this case, you're overly cold in the wintertime. As you go across the Rockies towards the prairies and Ontario, Toronto, Quebec, Newfoundland, they're not close to big bodies of water, which is why they end up losing this moderating effect. They're going to end up having much more extremes, really hot temperatures and really cold temperatures, depending on the season. More of the story there is stay on the West Coast. All right, so let's just apply this formula here to a few calculations. First question, how much energy is needed to bring 125 mils of water from 10 degrees Celsius to 50 degrees Celsius? Okay. So the experiment is quite simple here. We have 125 mils. 250 would be a cup of water, so it's about half a mug right now. So 125 mils, we know it's water. We know currently it's at 10 degrees. What I've done here is I've stuck it on a hot plate or in a microwave of some sort. I want to figure out how much heat energy do I need to put into this so that the particles are now moving fast enough here so that my temperature reading will read from 10 degrees and now it's going to say 50. I need to input in this energy. So far I've only given you the formula. Q is equal to mc delta T. Let's just punch through here. I don't know the mass just yet because it's quoted in volume, but fortunately for us, because it is water, we know that the density is actually 1 gram per mil. We actually defined density in that way so that water would work so nicely. In that case, their density actually changes depending on the temperature as well. We'll just pretend that it is just 1. So for water, you can say mils is grams. For other chemicals, not necessarily. So if this is oil, if this is some other chemical here, you might need to punch it through the density first. But there you go. The mass we're trying to heat up is 125 grams. The specific heat here is going to be on section 2 of your tables, some constant numbers that you need, so 4.18 or 4.2. That 4.18 is actually where food chemistry get calories from. 1 calorie is actually 4.18 joules, so water is going to heat up. You need 1 calorie to heat up that 1 gram by 1 Kelvin. And the temperature change that I want, technically because we're doing math and science here, we want to use Kelvin. But remember, because the increment on the Kelvin scale is the same as the increment on the Celsius scale, I can go final minus initial. I can say, what's 50 minus 10? Well, that's 40 degrees. You could have converted to Kelvin. You could have said, well, this is 283, and this one here is 323. But because this is always going to be a delta T, it's going to be 40 steps no matter what. So I'm going to be a little bit sloppy here. I'm going to say, yeah, the increment on Celsius cancels the Kelvin. So let's just crunch that through there. We have 125 times 4.18 times 40. This gives me here 20900. If it is grams, and specific heat is gram per Kelvin, this is probably going to be joules. I can divide it by 1,000, so 20.9 kilojoules. That's usually what we're going to do as we switch over back to the chemistry context. That's one way of asking the question, and they can play around with, if I transfer this much heat and this much mass, and the temperature changed by this, what's the constant? Basically, you can have one unknown in that equation. Let's do a little more interesting question here. This is more a conservation problem. This time I'm actually going to have 2 objects here. I'm going to start off with a hot object. Let's say this one here is my aluminum. We'll start off with, let's say, 50 grams worth. The constant I gave you earlier was 0.90. That's a constant specific heat that describes for the material how easy or hard it is to heat up. And let's say this block here is currently at 80 degrees. I heated this metal block up. It's a now sizzling block of metal. What I'm going to do is I'm going to drop this into just a beaker of water. In this case here, my water, it's going to be relatively cold. In this case here, I'm going to make it, that's saying 125 milliliters. That's half a mug from earlier. It's cold, so maybe I got cold water from the tap, maybe 10 degrees, and the constant was 4.18 joule per gram Kelvin. Experiment, as you might imagine here, is I'm going to take my hot block. I'm going to carefully just drop it into the beaker here. Because I have this temperature differential, I have a hot object inside a cold sort of basin of water, we're going to imagine that the heat will gradually escape. In fact, this is a nice hint for your test. When I actually do this experimentally, the biggest problem, let me write this down for you here, the biggest source of error in this whole chapter is heat loss to the surroundings. So because I have no way of making sure that this is perfectly isolated, I can't trap all the heat inside. Any heat that actually escapes outside, that's going to be the biggest problem. What we're going to do mathematically, though, is because we're sort of doing this ideally, we're sort of picturing a perfect world, we're going to make a few assumptions. So because I know the biggest problem is going to be heat loss in the environment, I'm going to pretend that's not a problem. I'm going to assume our system is perfectly isolated. Assume a perfectly isolated system. We saw this term yesterday. Isolated mean matter and energy can't escape. Imagine making the walls of this out of some really heavy-duty thermos, and it's a perfect thermos that whatever heat is sort of inside is sort of locked inside. We put a cap on top of it so no heat or no matter can escape here, so it's perfectly isolated. In sort of energy conservation in physics, we also need to worry about a guy called efficiency, because heat is not always transferred nicely, evenly, and quickly enough here. We're going to also pretend that's not a problem. Perfectly isolated, and let's assume 100% efficiency. Assume that the heat, if it wasn't 100% efficient, again, the same problem, heat might end up escaping and dissipating away, but let's pretend 100% efficient. Under those conditions here, we can then say, well, I know my hot block of aluminum has to, the water, because the aluminum is hotter, aluminum is going to lose heat, it's going to lose Q. The amount of heat that aluminum loses has to match up to the amount of water, how much heat the water gains. And under those assumptions, if there's no heat loss, if there's no other plus Q terms, I'm going to be able to apply that this one here is equal. Right? So under those two assumptions, we're always going to do that assumption here, and we're going to do a calculation from here on out. So let's try it out. Because these ones here are Q's, I can do my formula, mc delta t, mc delta t. Just be careful when you're doing mc delta t. On the left-hand side, we're doing the values for aluminum. So Al, Al, Al. And these ones here are for water. But we are just sort of implying that they're going to be equal anyways. So let's just crunch to the numbers here. I'm going to purposely leave a mistake, see if you can spot it. You can keep copying, I'll tell you when to stop. So we have 50 grams worth of aluminum. The constant I was given was 0.90 joule per gram Kelvin. Is the delta T for aluminum going to be the same as delta T for water? Hopefully you were to say no. Well, their starting temperatures are different, right? This is going to be from 80 to some final temperature. This one here is going to be 10 to some final temperature. Their delta T's are definitely not going to be the same. Just because the heat is the same, it's not necessarily going to change by the same amount on the temperature scale. So I'm just going to use whenever I see delta, I see final minus initial. So TF minus 80 has to equal to, for water, water we had 125 mils is grams, so 125 grams, 4.18 joule per gram Kelvin, and then same final minus initial, TF minus initial temperature was 10, right? Again, I'm going to purposely leave a mistake, but just keep following along here, see if you can spot it here. So 50 times 0.9, this gives me here 45 TF minus 80. This is equal to 125 times 4.18, gives me 522.5, again TF minus 10. Next step here is I want to distribute. I want to sort of get rid of this binomial problem here. So I'm going to get 45 TF minus 3600, 522.5 TF minus 5225. Okay. And at that point, you can stop copying because I mentioned I purposely left a mistake. If I then just sort of combine like terms, I add the 45 over, 522.5 plus 45. That gives me, don't copy the standards yet, 567.5 TF. And the other side here is negative 3600 plus 5225, 1625. So therefore, my final temperature is 2.9 degrees, or 3 degrees Celsius. Huh? How do I know that this is wrong? So I have my block at 80 degrees, I have my water at 10 degrees here, and I'm telling you by the time both of them hit 2.9 degrees, both of them will stop transferring heat. We would have expected, sure, the hot block to cool down, the water to heat up, but we wouldn't have expected water actually drops from 10 to 2.9. Like I mentioned, something has gone wrong in the calculation. Hopefully you're able to spot it here. It's actually a little bit sneaky, just right at the top. It has to do with this top part here. Yes, although we are saying in a perfect world these two heat transfers should be equal, there is a difference in direction here. This is the amount of heat that it loses, whereas water is how much it gains. So let's imagine a loss is a negative number. Let's say aluminum is out by $5, is minus 5. What I want to say, yeah, sure, equal and opposite. If this one drops by 5, I want water to gain by 5, but definitely the negative 5 one is not equal to plus 5. So to figure out, to kind of make sure they're actually equal numerically, not just, yeah, one drops and one gains, we're actually going to put a negative by one of them. By putting a negative on the other one, it flips the sign. Then I have positive 5 equals positive 5, Some people do always like putting the negative on the loss side. It really doesn't matter. You can multiply -1 on both sides and it can jump over. So let's just do it more correctly here. Let's propagate this minus down. That's why I asked you not to copy those last two lines yet. Let's do this properly now with that negative. This time it's actually supposed to be 522.5 plus 45. Hopefully we'll get somewhere between 10 and 80. That's sort of at least one mental check I can do. And then we're going to have, what's 3600 add 5225? That's going to be 8825. And then we have as our final temperature, cross our fingers here, 567.5. This gives me here 15.6 degrees, or give or take 16 degrees. So phew. At least the aluminum goes from 80 down to 15. It loses some 60 degrees or so. Water goes up 10 to about 16. Why was it, right, when I'm expecting between 10 and 80, why is it that water changed by only about 5 degrees, whereas aluminum changed by some like 60 degrees or so? Two reasons for that. You can see that from the formula here. One reason is there's a lot more water, right? So aluminum was only 50. There's a lot more material of H2O I'm trying to heat up. And the other big reason here is water tends to have a high specific heat. Water tends to have a high constant. So it takes more energy to actually heat up water than it takes to cool down aluminum. But there we go. For those reasons here, we end up with 15.6. So far, this one here is still a physics question because I artificially heated this block up and I drop in this cold substance. We're going to see in tomorrow's lesson, we're actually going to be performing a reaction. It's either going to be endothermic or exothermic. Because the reaction itself releases energy here, we're going to do a really simple calculation. Let's figure out what happened to the temperature, and let's see if we can backtrack how much energy was actually lost by the system. Let me do one last calculation with you here. All this formula is all nice, right? Q is equal to mc delta T, but all of it implies there has to be some temperature change. We just saw from the temperature time graph, especially for those phase change parts, the temperature doesn't change. So imagine going Q is mc delta T, and imagine putting in a delta T of 0. 0 will kill off all the M and C term. It would then imply, oh, the heat that's needed is actually 0. That doesn't make any sense. So just for completeness sake here, I'm just going to fix the formula a little bit. So we started off with the formula here, Q is equal to mc delta T. This works for the questions that we just did because there was no phase change. We're going to then just, for the purpose of phase change, during a phase change and only at a phase change, we're going to hide this problem here at the C delta T, and we're going to hide it in another constant called L. So I'm going to go for a phase change, Q is equal to M times L. This L here is usually going to be subscript F or subscript V, and what those subscript here, LF actually stands for the latent heat. Latent heat is just the name of it. Instead of specific heat, it's now called latent heat. It's the latent heat of, in this case here, F stands for fusion. Fusion is an archaic term for solid to liquid or liquid to solid. Or you can guess here, latent heat of vaporization. As I become a vapor, it's going to be liquid to gas or gas to liquid. So basically, I'm hiding away that problem with specific heat. And this is only true at the phase change. So for example, when I do my temperature time graph, I'm not going to fully work on this question for you, but if I have negative 10 degrees, there is some temperature changing. I use mc delta T for that part. Don't use this ml yet. You're going to start using this ml just for this phase change part, just to do the convert state 0 degree solid to 0 degree liquid. And then we're going to see in our question, if the temperature really did change, how much heat in context are we actually putting into the system? So let's end off with this question here. How much heat is needed to melt? Let's take that same 125 grams. This time I'm going to have it as 0 degree ice. 125 grams of 0 degree Celsius ice. I already am at the melting point, so I don't need to transfer in any heat to 0 degree water. So imagine heat is being added very evenly. I need to be given the specific heat. Given the LF, the latent heat is going to be 334 kilojoules per kilogram. That's just another constant you can look up. If it's not in the data booklet, which it's not, but you can look it up. Just Google it. So I want to take 0 degree ice to 0 degree water. I don't know if you can just picture how big this number is. This is already in the, first thing is in the hundreds, right? So far we've been dealing with 4.18, 0.9, right? Small numbers. It's already 334, but also is kilojoules. Although it does have this kilogram nature, maybe that'll cancel out. Let's have a look. So this formula is actually even easier than before, except for this notion of it needs to be kilograms. So probably easier, let's convert grams to kilograms. So during a phase change, Q is equal to ml as opposed to mc delta T. The mass I'm trying to convert here is 0.125. I converted that to kilograms, and therefore I can just multiply 334 kilojoules per kilogram. The kilograms cancel out. 0.125 times 334 gives me 41.8 kilojoules. All right. Just to put that number in context, okay, what if this 41.8, I needed that just to make 0 degree ice to 0 degree water, but what if it was already 0 degree water? What if I supplied an extra, a second amount of 41.8? How hot would the water be? So what if another 41.8 kilojoules was added? Previously it was added to 0 degree ice just to convert to 0 degree water, but what if I added to 0 degree water? What if the phase change isn't relevant anywhere? I want to just put this in context of sort of this temperature plateau here. So this time here, because we are water, the water can actually heat up. We can use our formula again. Q is equal to mc delta T. I want to know what my change in temperature is. Because I'm going to be using C as 4.18 joule per gram Kelvin, I'm going to convert this back to joules. So if I took 41.8, so that would be 41800. If you have unrounded, even better. So 41800. Let's imagine I took the same 125, so that's fair. This time it's going to be, well, it's mils for liquid, but it's still grams. 4.18 is my specific heat. When my temperature can change, what is my delta T? So let's take this 41800, or 41750 if you like, divided by 125, divided by 4.18. It gives me a delta T of 79.9. And just be careful, sometimes the initial temperature isn't 0. You still want to track delta T is supposed to be final minus initial. In this case here, we are actually perfectly 0. So water has actually gone from 0 to almost 80 degrees Celsius. That's almost close to boiling, right? So just to put it in perspective here, when we do this temperature time graph here, when we're saying temperature plateau, not only are we not cheating, heat is still being added, it's actually quite a ridiculous amount of heat. That amount of heat that I'm using just going 0 degree ice to 0 degree water would have heated my water up from 0 almost up to about 80 degrees or so, close to boiling. So it's quite a ridiculous amount. If you did latent heat of vaporization, even bigger, right? So I'm going to end the lesson there. If you have any questions, just let me know. Thanks, guys.